Welcome back. This is CS3510, L10B. The topic is on Knapsack. Knapsack is one of those problems that it's universal in the sense that every problem is a knapsack problem. We don't know this yet, but we'll see this, so it's a good segue into the next unit. It's also one of those things that has a dynamic programming solution for, but we don't, and it's one of those solutions that's hard to come up with on your own, like chain matrix. So it is another hard DP problem. And you know, stranded on an island, it would not be expected that you come up with a DP solution to Knapsack. But once you see the DP solution to Knapsack, every problem looks like a Knapsack problem. So that's sort of what we're going for. What is the problem instance? You're given a set of items which are encoded as pairs of values and weights. So you have such items, and you want to choose S such that you maximize the amount that you steal but you want to make sure you don't exceed capacity. So you're given this list of items, each with weight and value, and you're also given hopefully a large number W. And you want the property that you choose some of the items. You want it to be the case that the value of the items you took is maximum, but you are conditioned upon the fact that you are not allowed to carry more weight than the capacity that is given for you. It's kind of a simple problem, but there's an orthogonality here in the sense that you're maximizing one way and you're restricted in another. We did mention that there is not a greedy solution to this kind of problem, and there is no easy way to just choose the lowest or the highest and always hope that that works for you. Approximately, maybe, like that would be not so bad, but finding the optimal solution cannot be done in a greedy way. Simply because choosing certain items may exceed capacity that eliminates choices of other items, right? Every time you choose an item, some of the capacity gets eaten up, and that will prevent you from choosing other such items, right? Let's do a quick example. Suppose we have items of the form, let's say our weights are 1, 2, 3, and 4, so they weigh exactly that much, and our values are also 12, 17, 18, and 25, okay? And let our capacity be 6. So give me a set of items that maximizes the amount we can steal subject to the weight of the items is less than 6. Let's just try a few ones. We could try 3 and 4. If we were to steal 3 and 4, we actually can't. Now that I look at it, 3 plus 4 is 7, so we can't do that. Never mind. What about 2 and 4 then? 2 plus 4 is 6. We can steal item 2 and item 4. So what is 17 plus 18? Sorry, 17 plus 25. What? Yeah.
I think it's 42.
42, thank you. Sorry. I'm not doing, okay. What else could we steal? We could do 1 and 3. What is item 1 plus item 3? 12 plus 18 is, I can do this one, 30. Okay, what about 1 and 2? What is 12 plus 17? That's 29. What about 2 and 3? 2 plus 3 is 5, so
35.
17 plus 18 is 35? Okay, I believe you. Yeah. What else can we do?
1, 2, 3.
1, 2, 3. 1, 2, 3 is going to be what?
40. Yeah.
47, thank you. Okay. So is there any option we're missing there? Yeah, actually a couple. We could choose to steal no items. We could also choose to steal each item, right? So we could choose 1, 2, 3, 4. But these are the larger ones. And I'm looking at 1, 2, and 3 to be the biggest. So that's probably the optimal for this specific problem, right? So this is all Knapsack is you just want to choose the set of items. There are no duplicates allowed in this version. You get to choose the item or not choose each item. So you choose the items, and such that you don't exceed the capacity, right? Now notice though that 4, item of weight 4 is the heaviest, but it's the heaviest, but it also weighs the most. But choosing item 4 prevents you from choosing item 3, right? So if you choose 4, you must choose either one or 2 or neither, right? So choosing items prevents choices of other items. And that's like a core problem with Knapsack, right? You cannot choose part of an item. By the way, fractional Knapsack can be done in a greedy method. Suppose you are working with liquids and not solids, and you're allowed to choose portions of items. Why is fractional Knapsack solvable in a greedy in a way?
All you have to do is divide the value by the weight, and you just get how good it is.
Yeah, you can compute density, or like cost per liter or whatever, and then you take the most dense one until you run out of it, and then you take the next one, and then you take the next one. That fractional Knapsack can be done in a greedy way because it does not prevent choices, right? This does prevent choice because choosing one prevents the choice of another, right? If it was possible that you took all of 4 and then a portion of 3, that might be a better solution. It might not, but that would be allowed in fractional Knapsack, but it's not allowed here, and that's a very important part of Knapsack is that it prevents this decision. Right? So this is the Knapsack problem. Are there any questions about what the problem actually is? I'll mention again that Knapsack is a universal problem, and we'll see why later on. So it's a good segue into the next unit. But everything in some sense is a Knapsack problem. It's not just some contrived things about weight and value. Right, so we want a DP solution to this problem. Why? Because we're in the DP unit. So we need to talk about what is the subproblem going to be? Oh, before we do that, let's suppose we were to brute force search. What would be the runtime of brute force search? Yeah.
2 to the n.
At least 2 to the n, times some other stuff maybe, because who knows what it takes to compute sums and whatever. At least 2 to the n, which is not good, because, why is it 2 to the n?
Because for each item you can choose to either take it or not take it.
Exactly. If you consider 2 to the n subsets, even if, let's say, you ignore the empty set, that's 2 to the n minus 1, so that's not really changing anything. There's a pretty bad algorithm in brute force search. Can we do better? Not really, it turns out, as we'll see. But we can do something smarter, but maybe not better. So let's come up with a dynamic programming solution. Everything hard has to be at least 2 dimensions. And in fact, there are 3 and 4-dimensional Knapsack problems. But let's suppose we have 2 dimensions. I am asking about DP of some parameters to some parameters, right? What should those parameters be? We want to consider the problem as a function of subproblems in which direction, right? So your choices are really what? Yeah. So in fact, you're going to consider number of items. So we'll let one of the parameters be n, where smaller n here means you choose smaller items. Sorry, not smaller items. You look and consider less items. We'll define that more formally in a second. But what can the other problem grow as? Yes?
Capacity limit?
Yeah, let W be, as you can consider the subproblem as if you were pretending to have a smaller capacity, and that can influence a problem of a larger capacity. So we're going to let DP be a function of W and N, okay? Now what should this actually be defined? And we want the English sentence for this. Max you can steal with capacity W, only considering items 1 to n. Now that's W comma n is going to end up being the final answer, right? Now, like house robber, it's not necessarily true we will steal the nth item. And here we, in fact, did not, right? But it's considering items 1 through n. So when we make this as a subproblem, n minus 1 will be considering only items 1 through n minus 1. And then as we consider the next problem, the next item, that may change some of the subproblem, right? That's what we want to do. Right. So let's formulate this a little closer. Let's try to expand upon what's the dependency on the subproblems, the optimal substructure. So for each item, you're in consideration of the nth item, right? Let dp of ij, let's just do wn first. Let's do wn. Let's say you do not steal the nth item. What do we know about dp of wn if you do not steal the nth item?
It's dp of wn minus 1.
Yeah. If you don't steal the nth item, that's the same solution as if you had never even known the item was there. Okay? And in fact, there are sometimes you cannot, when can you not pick item n? Yeah.
When it would put you over the weight limit.
Yeah. And there's a worst case that it can put you over the weight limit in that it just exceeds your, not even your current remaining capacity, but just the capacity in general. So this can also happen when the Wn exceeds just W, right? If it's just too big, you could never hold it. That also is the case. You could not pick the item, right? Now, if you could pick the item, what would the function be? Well, if you could pick the item, this would be equal to, you would at least earn the value of the item, right? So you would walk out of there with at least Vn. Does this one work? Yeah. You would walk out of there with at least Vn, right? Plus some subproblem that corresponds to the choice of the previous items. So what should that correspond to? It's going to be dp of something. Yes, suppose we do steal item n, so we have value n. Yes?
dp of w minus vn.
We need to get to that in a second. Let's talk about the w part in a second. I'm asking, if we are choosing to steal item n, we have a subproblem considering what other items? Yeah. So it's something of the other n minus 1 items, whether or not they're chosen or not. So we know that this parameter has to be n minus 1. But understanding what the capacity here is going to be is a little different, right? We know that item n has capacity Wn, sorry, it has weight Wn and value n, right? Vn. And we know that we earn Vn by stealing it. So our capacity, in fact, does change in the parameter here. Because when we choose to take item n, it increases, it fills in our capacity, right?
It reduces the effective capacity for the rest of your items.
It's as if, I guess, I would word it the other way, in that if you, the other n items you stole from the previous n minus 1 somehow were able to be situated in a way in the capacity, weight-wise, that did not consider Wn. So somehow you were able to steal some number of the other n minus 1 items without overflowing to, at most, W. So the capacity ends up being W minus Wn. Because what that is, let's say you had capacity 10, and the last item you choose to pick has weight 2. That means the other items somehow were able to fill in up to weight 8. Right? You were able to choose some subset of those items and not exceed weight 8, because when you do choose item 10, you do choose item n, you do go from 8 to 10. So somehow, because it had weight 2. So everything else somehow had to be able to fit into weight 8, up to at most weight 8, whatever that happens to be. Okay, that's it. That's Knapsack. Let's rewrite it, but any questions on it? Let's make it more clear. Let dp of ij be up to capacity I and items 1 to j, okay? So we know two things are going to happen, right? We're going to just take the max of these two in the first case. Is it cheaper to steal the nth item or not? This is going to be the max of dp of w minus wi, comma, j minus 1, plus vj, if you choose to steal the item. If you do not choose to steal the item, this is going to be dp of w, comma, n minus 1. Sorry, I minus 1? Nope. J minus 1? Sorry. Okay. But sometimes you don't get to choose the max of those two because the item takes over for you. So if it's the case that the jth item's weight exceeds not even your current capacity, but the capacity at all, then you just don't consider it. So this will just be hard-coded to be dp of w, comma, j minus 1. Hold on. This should be, sorry, no. I. There we go. Okay. There we go. Anyone notice that, right? Question?
There's one more W that needs to be replaced with I, it should be.
Yes. Thank you.
And then also the subscript next to it should be J, not I.
WJ, yes, thank you. Right. So you're in consideration of the jth item. It updates your weights, and it updates the number of items that are under consideration. So you take the max of do you consider the item or not consider the item. Again, in DP, everything is a max or a min or a sum or a product or whatever over all possible combinations. So this is the case you do choose item J, and this is the case that you don't. If you do choose it, again, you walk out with a value Vj additional, and whatever you could steal from your reduced capacity, only considering J minus 1 items. And if you don't steal it, it's as if you had never considered the item to begin with, right? Now, if the item is too heavy, you can't steal it, so you have to consider this case. So we would only consider this case if it is that Wj was less than or equal to W. Question?
Why have this hard-coded stock? Isn't it the case where if weight is negative, then it's,
Sorry, what's hard-coded?
why have this hard-coded?
This, you mean? Sorry. Again, with the eyes?
It seems like a optimization that would,
Sorry, what are you referring to? What are you saying the hard-coded?
the hard-coded if we can't choose J at all.
You mean the first case where the weight exceeds?
Yes.
Um,
Is it just so that we don't attempt to index into an array?
yeah, you want good programming, and there are variants of Knapsack that build upon this that only really work if it's defined that way. Sometimes things are pedagogical. Sometimes things are not important and for fun, and sometimes they are important. And this is one of those times I think that variations of this algorithm may not handle. If Wj exceeds the current capacity I anyway, you're going to index into something negative, and you can't rely on your implementation to handle that. And just don't do it. Better programming would just not do an array out of bounds instead of trying for an array out of bounds and then making sure you accept it. A better thing just to make sure it never happens.
I guess it just seems analogous to previous problems where we don't worry about the programming details. And so I was asking.
But in each previous one we've done, we've been very careful to make sure that we don't call an array out of bounds as well. You don't want your code to have undefined behavior. And sure, there's an extra if statement here, but it doesn't really matter. Right? As long as it looks right. So, more questions? Now that's Knapsack. Once you learn Knapsack, you memorize that recurrence, and then it shows up all the time. It's got a lot of moving parts because there's I minus WJs, there's a conditional, J minus 1, when do things happen. But if you understand what the meaning of things are, where this is choose the item or don't choose the item, this is how the recurrence works, right? Are there any questions on this before we implement it real quick? Yes?
How do we get the capacity that we actually used at the end of, say, like?
Oh, great question. The capacity we used at the end.
Yeah.
Well, consider that, I see. So suppose that there is, before I answer your question, what should be the item of the rate that we return?
The nth item, like.
What element of the table do we return as a final answer? Yeah. And are you asking, what if we choose a set of items that's optimal that does not use weight?
Right, because we never actually keep track of the running weight that we're using.
Correct.
It's just handled for us.
Yes. And what will end up happening is if you choose the nth item, and let's say you choose an optimal set of items, yet you still have capacity left over, yet you have not enough capacity to fit any item left in. It is true that this will contain the right answer, but so would, for example, dp of w minus 1n. and w minus 2n may also contain the right answer. So why do we return this? It propagates for us when we do this a bunch of times.
So regardless of if we have capacity left over, that's always going to have the right answer.
Yes. Now, some other cell of the table may also have the right answer. And recall when we did longest sequences, the answer, the end of the longest common subsequence may not have been at the last character. But that's okay because of the way the recurrence worked, it pushed the right answer to the bottom corner anyway. Same thing will happen here as you observe the computation. This recurrence, I think, is really beautiful because it hides a lot of questions like that. And then once you actually view it, you're like, you see how it's handled. And I don't know if it's a good thing or a bad thing that it disguises that, but it does solve the problem for us. So if you just trust it, it'll work. Right? And we'll do that in the implementation. More questions? Let's implement it real quick. This version of Knapsack is sometimes called 0-1 Knapsack because every item is either chosen or not chosen. You do not, this is in contrast with another version of Knapsack we'll talk about today, which is Knapsack with duplicates, in which you can choose multiple of the same item. There's infinitely many copies of each item. But let's just suppose you either choose the item or don't choose the item for now. So we'll call this 0-1 Knapsack, and it takes as input a W, an array of V1 to Vn, and an array of W1 to Wn, right? And let our dp of, let's say, 0 to W, 0 to N be all zeroed. What are our base cases?
Weight equals 0, set everything to 0, or number of items equals 0, set everything.
Yes, okay, there we go. So if dp of I comma 0, if 0 is in the last index, what should that correspond to?
You can't take it yet.
Yeah. If the index, the second index corresponds to items 1 through j, having a 0 here corresponds to items, not even considering item 1. So there are 0 items for consideration. There are no items for consideration, you can't steal anything. This will be 0.
Do we need that in the pseudocode if we already started the array as zeros?
So I did mention this for the previous times, but it's one of those implementation things, and it's just polite to write the base cases out. When you actually implement it, you can hope your computer architecture zeroes things out for you. It may not. I don't know if there's something exotic that wouldn't and just leaves random memory hanging out there when it allocates it back to you, and then you read it. Sometimes that happens, right, in raw C. But when you're doing the construction, it's best to write the base cases out because it's pseudocode. So you need to tell the reader what the base cases are. So in a mathematical writing context, yeah, it's necessary. So let's suppose we're considering items 0 through n, and we have 0 capacity, right? We cannot carry anything. If we can't carry anything, we can't choose to steal anything. Assume item weights are positive. So, well, of course, the max we can steal is 0 as well, right? So now we just loop over the array and fill it in. For j in 1 to n, for I in 1 to w, if we can't even consider the item, then dp of I comma j takes on the max of the two options we have, which is either we choose to steal it, so I minus wj comma j minus 1 plus vj, or dp of I comma j minus 1. And if we can't steal it, then dp of ij just goes to the option as if we never considered it. And then what do? We return dp of w, n. Done. Okay, easy. What's the runtime? Why?
It's just 2 loops.
Yeah, 2 loops. Memory is that size. Space use is that size. Constant, a bunch of stuff in there. Maxes, mins, subtractions, whatever. And that's how it goes for most of the time, DP, where you just really, it's always the size of the table times the time it takes to fill in a single cell. Sometimes that's not constant, as we saw with chain matrix, but here it is. So it's just the size of the table, which is Wn. Is that good or bad? It's not bad. Is that, here's another question. Is that exponential or polynomial? It's exponential. Why?
Well, it's 2 variables multiplied by each other.
And m could be polynomial. It would be a multivariate polynomial.
Very drastically different numbers.
That's still not enough to say that it's exponential. A polynomial can be in terms of multiple numbers. A multivariate polynomial, right, is not a problem. V plus e is a polynomial runtime, is linear runtime, in fact. This is a very difficult question, so let's take a second to ponder.
Because W has to be big?
Not necessarily. You don't know anything about the w and n that are given.
So it could be exponential.
I mean exponential in what? Sorting algorithm works at 1,000,000 elements or 1,000,000,000 elements. We don't say it's exponential, it's still n log n, right? What do we measure the algorithm runtime in?
Operations.
Operations, that's the number of steps it takes, but it's a function of what? The notion of polynomial or exponential is not a literal runtime in the sense of you have n log n or something, but it's in fact a classification of like good and bad. And what do we measure the runtime of an algorithm in? An algorithm is always measured. Oh, let's fix it on graphs, for example. Why do we call V plus E linear time? BFS, DFS take linear time. Top sort takes linear time. Why do we call them V plus? Why do we say V plus E is the actual runtime, but why do we say it's linear?
It's like asymptotically linear with the parameters that we have.
The input. The input is of V plus E. It takes V plus E. The size of the input is V plus E. So it takes approximately the size of the input. You measure an algorithm not in made up letters and numbers, but rather function of the input size, right? So how big is the input here? Suppose each VI and WI are constant size, but W is not. How big is W? What? W. Yeah, how big is you're given an integer and 2 arrays.
The W is of size like log W?
Yeah, so the input size is approximately log W plus approximately constant sized elements, but yeah.
The number is W. You can store it with bits.
Log W. If your input is size log W plus 2n, but your runtime is O of W, Wn. In fact, this is an exponential algorithm. This runtime is the runtime of this algorithm is exponential in the size of the input. So this is not there's no 2 to the n, but it is still exponential. What's the difference between the difference between log W and W is as big of a difference between, I don't know, k and 2 to the k. Those are and in fact, actually there was a paper on this. Students commonly overestimate how big log is, right? There's only 10 to the 80 atoms in the universe, so log of the number of atoms in the universe is at most like 80, something like this, right? So log is incredibly small. This is incredibly concise of a representation. That is a function of W, right? Now suppose I had said that the number of bits of W was k. Then we would say that the input is of size k plus 2n, and the runtime is 2 to the k plus n, 2 to the kn, right? Now if I write 2 to the something, you're like, okay, that looks exponential, so now that's exponential time. right? Many people don't think, like, it's hard for them to understand that knapsack is an exponential time. Even this DP algorithm is exponential time. It's a better exponential time than brute force search, but it's still exponential. It's still pretty slow. And if you think about it, you can represent W in log W bits, but the dimension of the table is W. So the dimension of the table is exponential in how small W is, right? It's very, very, very small. 2 to the 100, for example, let's say W is 2 to the 100. You could give only 100 bits to describe W, but the table size would be so big you couldn't fit it in the universe, something like this, right? A table of size 2 to the 100 is much bigger than the input of size 100 bits, right? The reason I mention this is, like, it is not known if you can do better than this. Like, can you find a better dynamic programming algorithm or any algorithm that solves knapsack faster than WN? Actually, yeah, but can you solve it faster than exponential in the size of the input? Answer is probably no. And if you could solve it faster, you would win $1 million. It's like, this can be solved faster if and only if P does not equal NP. No, the other way, P equals NP. So finding a better algorithm can award you a lot of money. We'll talk about this next unit and why we don't think we can solve this faster. But the fact that it's exponential should not be surprising, given the stuff we'll cover later. But you should also be convinced after that you can't do better. That's sort of the moral. Questions on the runtime. Does everyone understand the argument I'm making? Log W versus W. Right? This is not a good runtime. You just can't see two letters and say that looks polynomial because they're next to each other. Although that's how every algorithm has worked so far in every class. Let's do an example. So we do it for the previous items that we had. Our items, we can consider no items, items 1 and 2, items 1, 2, and 3, items 1, 2, 3, and 4. And we consider our capacity to be, as it increases from 0, 1, 2, 3, 4, 5, and 6. Right? And we know that if the capacity is 0, or the items are 0, then these are all zeroed out. But now we need to fill in the table in the correct order, right, to make sure that things that are smaller are previously called. So the for loop is not going to be something complicated like chain matrix. It's going to be simple two increasing loops, right? So let's just go this way. What should this, we have capacity 1 and we're considering item 1. Now conveniently, I'm also setting the weights to 1 so we don't have 3 things moving around. What should this value be? Let me rewrite the value. So can you read to me the values?
12, 17, 18, 25.
Okay. So if we have capacity 1 and we are only considering items 1, we could steal it. So the max we could earn is what? Done, right?
Wait,
Question?
we have capacity 1,
Correct.
so we can only have a max of 1.
We can steal items that either weigh 0 or 1. And we're only considering
Oh, right, yeah.
items, no items, or the first item, right? So 1 pound weight we can hold, and this item happens to weigh 1 pound, so we can walk out with it, okay? Now suppose we're only considering item 1, but our capacity increases. Nothing exciting there, okay? We can hold more, but there's only one thing to consider. Fine. Suppose we're considering items 1 and 2, but we can only hold weight 1. We can still only consider the item of weight 1, so this is also going to be 12. Now, if we could consider weight 2, we can choose between item 1, item 2, but not both. So which one is heavier, item 1 or 2? Yeah. Now, let's suppose we can consider we have capacity 3. We could choose 1, 2, or both, in fact. So which one do we take? Yeah.
29.
Just to illustrate, this one is what cell of the table is that? That's going to be dp of the weight, capacity is 2, and we're only considering items 2, right? So we're comparing with what two cells? We're comparing whether or not we did not choose item 2, and if we didn't, we chose the max of 2 options. If we don't choose item 2, it's going to be dp of 2 comma 1, right? And if we did choose item 2, it would be dp of the weight of item 2, which is 2. So it'd be 0 minus, 0 comma 1, right? So what cells does this one reference? It's going to be, had we just considered the same capacity but not choosing it, so it would be that one. Or if we had not chosen it, we would only be considering the first item as well, but we would have no capacity, right? So it would be here. Unlike longest sequences where you can really visualize in the table where things work, it's going to be a bit more difficult as these sub-problems increase, right? Let's continue. If the capacity goes up, can you choose anything bigger? No. And double check me on all this, right? Let's suppose you have capacity 1, but items 1, 2, and 3. You can't choose anything but item 1. Now, if you're here, if you have capacity 2 and you can look at items 1, 2, and 3, again, what's the max you can steal? You can't steal item 3, so you're just going back to this case. Right, so that would in fact be 17. And notice that this one references this one, right? This is dp of 2 comma 3. But since W3 is equal to 3, that exceeds our current capacity of 2. So we cannot choose the item. So then this must simply be equal to dp of 2 comma 2, right? So we just literally look there, and that looks for us. So that one looks there, right? What is 3 comma 3?
29.
If we don't take the item, it's 29. Or we can choose to take the item, but then we can consider no capacity of the previous. So we would be here, considering items 1 and 2 with no capacity, with the value, which is 18. So we can do 0 plus 18, or we can do 29. So this one looks here, and it also looks there, right? As we continue the capacity, does anything change? Yes. This is 30. Why? Yes. So we can either choose 29 by not considering item 3, or if we do consider item 3, we are looking at the value of it, which is 18. So it could be 18 plus 12, right? So we either consider this one or 18 plus that one, right? So it's 30. 18 plus that one is bigger than that one, right? What comes here? 35. Okay. Yes. Okay, 35. We could either choose 29 or we can choose 17 plus 18, which is 35, which is going to be this one. Yeah. I'm not going to draw more arrows, but we see the recurrence, right? What comes after here?
47.
Correct. And in fact, that's going to be our optimal, as we'll see, right? This considers items 1, 2, and 3. So you can either choose 29 and not consider item 2, or you can consider item 3 and then have capacity left over for items 1 and 2, which would put you right here, in fact. Because that's the problem that considers the max you can steal with capacity 3 and items 1 and 2 under consideration, right? And as we fill in this array, this is going to be, I'll just tell you it's the same, 17, 17, 29, 30, 35, and 47. Right? This one considers that one considers that one. In all cases, it works. Right? That's our answer. Done. Questions? Okay. That's how Knapsack works. Let's consider some variants of Knapsack. Recall the Knapsack recurrence. It was dp of I comma j ought to be either, if you don't consider the item, it's dp of I comma j minus 1, if Wj exceeds I. Otherwise, it was the max of dp of I minus Wj, j minus 1, plus Vj, or dp of I, j minus 1. Right? And this is if Wj is choosable. Notice that this is for 0-1 knapsack specifically. Suppose we wanted to make a recurrence, but with the only, for knapsack, but with the only modification was that it was repeatable. For each item, there exists infinitely many copies of each one. Let's consider what's the smallest way we can modify the recurrence to have this property be true. So we want dp of ij to be the max you can steal, considering capacity I and items 1 through j. But we don't want to restrict ourselves from, if we consider an item, we don't want to disallow it from being considered again. We want there to be infinitely many copies of each item. And if we consider the way the dp table looks, right, so this would be 0, 1, we had some cell here, and it would either consider not looking at the item at all, 0 copies of the item, or it would consider something, again, in the previous column, but at some lower capacity, right, plus a value. So it would be something like that, right? But we want to consider the case where we're allowed infinitely many copies of each item, right? So it could be the case after you choose an item, you get to choose it again, and again, and again. So we need to modify our recurrence in an incredibly small way. If we choose the item, we don't want to prevent choice of it again. What is the smallest change that could be made to our recurrence to allow this? Yeah.
In the bottom left, replace j minus 1 with j.
Yeah, that's it turns out. J minus 1 is forcing you to consider items 1 through j minus 1. So if we were to repeat this and consider the following modifications, if we don't choose the item at all, we can't choose it. There's nothing we could do about that. But if we can choose the item, we should allow ourselves to choose it as many times as we want. So here we would consider the capacity as if we had never chosen that item. Here we would put j minus 1 because we would consider items 1 through n minus 1. But we want to allow ourselves to consider the item again. So instead of j minus 1 here, we're going to put a j. We're now going to increase the amount we're stolen by this Vj. And similar here, if we don't choose it, this is just going to be dp of I, j. Let me double check. Correct. You can't have that recursive thing. Right? The difference here in this j is what allows you to consider a subproblem of previous things. And were we to fill in a table, this would be 0-1 knapsack, this would be with repetition. What the difference would be is that a cell here may reference the previous column by not considering the item, or it may allow itself to consider the item multiple times. And what that means is instead of looking at the previous column, you look at the same column but above, which may in itself consider something above, and so on, right? So this is where you would store the j value, right? Because that's we're not looking at j minus 1, we're looking at j. So it would in fact be the same column, but something previously computed above you, right? This corresponds to, you're considering the same number of items, but with a smaller capacity. That's exactly what this is, right? And then that may consider the same number of items with a smaller capacity, and so on. So that's the only modification you have to make knapsack without repetition be knapsack with repetition. So the -1 can change the solution entirely. What's the runtime? Yes?
It's still wn.
Yeah, nothing changed. Exactly the same, everything. I don't think we could, the answers in the table would change significantly, but the code, nothing else in the code would change at all. Not even a little. Okay, that's knapsack with repetition. Any questions on that? Yes?
Wasn't it supposed to be without the -1? DP?
Double check. So it is still the case that you can not choose it. So we only want to modify that if you do choose it, you are not restricting yourselves to choosing it again. That's why this case and this case both are still -1, because they consider not choosing it at all. Or maybe not choosing it like a third time or something, right? You would choose it 3 times through this one, and then this one would just be the 4th time, which would be, it would not be chosen, right? Something like this. But having this here, again, this is why it's important to assign an English sentence to each cell of the table. This is, had you had capacity of I minus wj, only considering items 1 through j. But this is after you've chosen the jth item, so you could just consider items 1 through j, means you're considering it again. J minus 1 means you're not considering it again. J means you're considering it again. Now, if you had never chosen it, then of course it's going to be J minus 1, because that means it's not J, so it's something previous. Yes. Again, one of those little details. Right? Questions on knapsack with repetition? We can pretend I re-implemented it and filled in a table. Okay. Maybe we can't increase the time. We can't speed up the time on this variant. But we can actually, it's kind of surprising that with repetition, you can actually speed up the space. So this is a 2-dimensional table we have for knapsack. I claim that we can do it with a 1-dimensional table. We don't really need to consider the increase in items as we had increased. We don't really need a 2-dimensional table to consider the increase in both items and capacity. We can just consider all items at the same time and consider the increase in only in capacity. So rather than consider prefixes of items, let's just do it in a harder way that considers all items at the same time, but an increase in capacity. So let dp of, and we'll do this in 1 dimension, 0 to w, be, what should this be in English? Not the recurrence yet, but just in English.
Max value combination.
Yeah. So dp of, sorry, let me say it this way. dp of I in English would be what? For I is,
Max value combination under that capacity.
yeah, I guess, max considering capacity I and all n items. Okay. So let's just consider all the items. What would the recurrence be? And that's, again, this is with repetition, not without repetition. It's going to be a max of something. So again, we start in primitives. The max what, though? In human words, we want the max you can steal. So what would that be?
Max value every combination.
Kind of.
You, for every value that you can steal, add that value, or start with that value, add.
I'll help you out. Let J range over the items, and let Wj be choosable.
Right, so it'll be dp of I minus wj, and then plus vj.
Done. For every item, the loop goes over all the n items, and it chooses the max which of those for each one. Okay, that's it. That's knapsack with repetition in 1 dimensions. What is the space? Now, space, difficult. We don't want to talk too much about space complexity. It's weird. It's difficult. Previously, we did space of Wn, right? Here, we're doing space of what? Yeah. Now, is that any more efficient? If W is still exponential. The size of W, if it takes log bits W in the input and you have a table of size W, that's not really any smaller. It's one dimensional, but not in the dimension that matters. Right? It doesn't really matter. It's not a good speed up. What's the runtime?
Same.
Why?
Because instead of doing 2 loops for a 2-dimensional array, we just have a 1-dimensional array, but every time we add new entry, we have to go through the array and iterate.
Yeah. Previously, it was like W and something like this. It took all of 1 to fill in each one, and we had this much. Here, though, we take W cells of the table, and it takes how long to fill in each one. We have to consider all n items. So this is the same thing. So it takes non-constant to fill up the table here, but you end up with the same runtime for both. So this does not speed up time at all, but it does speed up space in a way that doesn't matter. And in fact, I would even consider this a worse solution. Even though they're asymptotics of each other, one is less clear why it works. So space is cheap and free, and don't even care about optimizing it most of the time. When you do computation, you always get the space back, okay? When you call free, you turn off the computer, the space is, you get to reuse it. But you'll always get the space back, but you never get the time back. So time as a metric is of several orders of magnitude far more important than ever caring about space. So I would rather take a worse space efficient algorithm if it was cleaner to explain than something that's more space efficient, but in fact perhaps has a worse runtime even, right? In practice, if this is thrown away in the corner of a library somewhere, then who cares? But if we're trying to communicate things to each other, I think I would take the worst one, right? But this is how you can do Knapsack with quote-unquote linear space. Not really, but less space at least, but the same runtime, right? There are other variants of Knapsack. You can imagine a variant of Knapsack which did not allow infinitely many options for each item, but perhaps allowed you to choose each item at most some given number of times. You could solve that with perhaps a 3D knapsack, or you could perhaps throw in some ifs and counters in there and figure this out, right? Are there any more questions on Knapsack? Knapsack universal problem. We'll see every problem is a Knapsack problem in some sense. Why that is, you'll have to wait like 2 lectures. But any questions? All right, have a good weekend.